In this video we discuss the conservation of mechanical energy, and what that means is that the energy before an event happens equals the energy after the event happens. In our textbook they say energy final equals energy initial, and the mechanical energy that's discussed here is kinetic energy and gravitational potential energy. It's 1/2 mv squared plus mgh for the final equals 1/2 mv squared plus mgh for the initial. So, these two sets of energies will change, but the total overall energy will not. So here's an example here where a bobsled's going down a hill, and if you look at this far right-hand column, you'll see that the energy stays 600,000 joules the whole time, no matter what position they're at. At the very top, where their velocity is 0, they're going 0 joules. The potential energy is 600,000 joules. The potential energy is mgh, that's 600,000 joules. Now as they go down this incline, you'll see that they go faster and faster and faster, so the kinetic energy is becoming larger and larger and larger. At the same time, the potential energy is getting smaller and smaller and smaller because the height above the ground is becoming less. But you'll notice over here the total energy, which is made up of kinetic energy plus potential energy, has stayed constant. So that's what the conservation of energy says, is that the total energy stays constant. So if we look at this example of a roller coaster, we're starting and our roller coaster is up and down, and its energy is changing positions, or changing types of energy. It's going from kinetic to potential. But you'll see that it goes down, it speeds up, slows down, comes around the loop, and you'll know, but the total energy at any point along that roller coaster stays exactly the same. Now remember, we're ignoring all air friction and friction of wheels and so on. Here's another example of conservation of energy. We have a skater who's going to be skating up and down, back and forth. You'll notice that the energy that reaches up there, the maximum energy reaches up there, is the same right there. That maximum height is the same on both sides. So that height, that maximum height, is the same all the way across here because you're not losing energy to friction. I can even change this. Because we see that the height stays exactly the same. The energy is the same the whole time that the skater's moving. The energy stays exactly the same. It just transfers back and forth between potential energy and kinetic energy. Now, if we look at the graphs of that, you'll see with these bar graphs that this skater's moving back and forth, and the bar graphs are moving up and down. The total energy is staying exactly the same. The kinetic and potential energy are just changing the maximum and minimum values, and the total energy is staying exactly the same. Now I'm going to add a little bit of friction here just for fun and see what happens. You'll see that the thermal energy starts growing as this person goes back and forth, and the thermal energy will keep rising until it reaches the total energy, and the kinetic and potential energy, you'll see, are dying out. And in this case, it's still conservation of energy, it's just that kinetic energy and potential energy are conserved. All the energy is lost to thermal energy, so it goes back and forth until the thermal energy reaches that total energy, and we still have conservation of energy, but all that energy goes out as heat. Okay, I've taken the friction off so that this skater will go back and forth forever. And here's an energy versus position graph. And you'll notice that the olive color total energy is the same all the way straight across no matter where the skater is. This total energy stays the same all the way across. This green here is the kinetic energy. You'll see it's its maximum in the middle. And the blue, the potential energy, is maximum at the end, so that's due to the height. If we do this graph, energy versus time, we get something that looks like this. Alright, now we can take a look at an example. Motorcyclist is trying to leap across the canyon shown in figure 6.8 by driving horizontally off the cliff at a speed of 38 meters per second. Ignoring air resistance, find the speed at which the cycle strikes the ground on the other side. Now we can use kinematics for this, but we are going to use energy instead. So we realize that the initial energy and the final energy have to be the same. Initially the energy is some value, and finally the energy has to be some value. So we go ahead and plug in our values for the final position and the initial position. Now, what's nice here is the final position is 0, so this all goes away. And we can plug in our speed of 38 meters per second here. Oh, and the other thing is the masses all cancel. Our initial speed was 38 meters per second. Our initial height, um, we are given as being 70 meters. Our final height is 35 meters. And our gravity is 9.8. And we plug those values all in, and we end up with a value of final velocity of 46.2 meters per second. The tallest and fastest roller coaster in the world is now the Steel Dragon in Japan. The ride includes a vertical drop of 93.5 meters. The coaster has a speed of 3 meters per second at the top of the drop. Neglect friction and find the speed of the riders at the bottom. So again, this is total energy in the beginning equals total energy at the end. And so we have this same setup here where we have this 1/2 mv squared equals mgh. For the final position, 1/2 mv squared equals plus mgh for the initial position. We plug all our values in, and we can go ahead and solve for our problem that we want. We know our final height, or our final height is 0, so this whole thing goes away. We know our initial height here is 93.5 meters. Masses all cancel. Our final velocity is what we want to solve for. So we can just go ahead and plug in our values, and we end up with an answer of about 43 meters per second. Now at this point, we want to take into account a non-conservative force such as friction and see how to handle that. And it says in the previous example, we ignored non-conservative forces such as friction. In reality, however, such forces are present when the roller coaster descends. The actual speed of the riders at the bottom is 41 meters per second, which is less than the 42.9 meters per second that we calculated. Assuming again that the coaster has a speed of 3 meters per second at the top, find the work done by the non-conservative forces on a 55 kilogram rider during the descent from a height HO to a height HF, where HO minus HF is 93.5 meters. So that difference in kinetic energy, that change in kinetic energy that we can calculate when it's going 42.9 meters per second with no friction, now it's going 41 meters per second with friction. That change in kinetic energy, that difference in kinetic energy that we can calculate, will just be the work done by the force of friction. Another way of looking at that is if you think of the non-conservative force as the difference of the total energy final minus total energy initial, that will give you the work done by the non-conservative force. Find both kinetic energy and potential energy at the bottom, and then kinetic energy and potential energy at the top. They're supposed to be equal to each other when you do not take into account the non-conservative forces. But now that we are, the difference between the total energies at the top and bottom is due to the work done by this frictional force, and so we can calculate it by using this formula. So we simply just plug in our values, and we end up with an answer of negative 4,400 joules. We have another example we can look at here. A 0.2 kilogram rocket on a fireworks display is launched from the crest and follows an erratic flight path to reach the point P, as figure 6.21 shows. Point P is 29 meters above the starting point. In the process, 425 joules of work is done on the rocket by the non-conservative force generated by the burning propellant. Ignoring air resistance and the mass loss due to the burning propellant, find the speed V final of the rocket at point P. So again, you can look at this as if you can say the work done by the non-conservative force is equal to the total energy and final minus the total energy initial, and that should end up being negative 425 joules. Actually, in this case, it's going to be a positive 425 joules because the force from the rocket is in the same direction as the displacement. So here we have this idea that the work done by non-conservative force is the total energy at the final position minus the total energy at the initial position. Plug in all our values, and you'll notice that we have 425 joules here plugged in for the work done by non-conservative force. You just plug in all your values, and you should end up with a final velocity of 61 meters per second. I also suggest that after reviewing this video that you read the textbook dealing with this, the idea of the section 6.5 and 6.6 that deals with these ideas.